Alrighty, everybody, welcome back. Today we are going to do a few fun things. We are going to take a more thorough look at antiderivatives. So I gave you a handful of antiderivative formulas in class last time. Today I want to show you a slightly more formal treatment of what antiderivatives are. And then we're going to march forwards, armed with that knowledge, into the fundamental theorem of calculus. So let's get the screen share on. This is MAC 2311, section number 004, which is Calc 1. And the date today is the 30th of March, 2022. As promised today, more on antiderivatives. And FTC. Antiderivatives are exciting in the sense that at a glance, it seems like finding an antiderivative should be exactly as hard as finding a derivative. Because remember, an antiderivative, we say big F is an antiderivative for little f if big F primed of x is equal to little f of x. And sometimes we qualify where this is taking place, like over some collection of x values on some interval, but in general, this is the way to think of it. So it appears at a glance to be the case that finding antiderivatives should be just the process of taking a derivative run backwards. And that is true. But that might lead you to the belief that calculating an antiderivative is equally as hard as calculating a forward derivative. That is not true. Many functions out there we can differentiate in the normal sense, but we cannot anti-differentiate. So taking an antiderivative from a global perspective is actually much harder than taking a derivative. That's a fact that will slowly become more and more apparent to you as we go through the procedures. But what I want to show you here today is just the sort of fundamental rules. I want to expand that collection of antiderivatives I gave you last time, help you understand where some of the rules come from. And that way we have enough kind of examples and comfort that we can start doing some real examples with FTC. So first, a couple theorems. If big F of x is an antiderivative for little f, then so is big F of x plus c for any constant c. This is not a difficult theorem to prove. We're going to prove it. It's going to take 10 seconds. But it is the source of many lost points on exams, especially at the end of Calc 1 and the beginning of Calc 2. You will, at various times in homework and on tests, be asked for the most general antiderivative of a function. And in that context, we need to remember to slap on an arbitrary constant after finding our sort of specific antiderivative. The proof, like I said, is incredibly quick, so we'll go ahead and do it. Since big F is an antiderivative for little f, we know big F primed is little f, thus big F plus plus c primed is big F primed of x plus the derivative of a constant, which is 0, is little f of x, because big F primed is little f. And that's it. So big F of x plus c is also an antiderivative for little f. I'll say little f of x. Right. That's it. So some vocabulary. When we ask for the most general antiderivative of a function little f of x, one should first find an antiderivative big F of x, and then give the answer that big F, which you found, plus c. This is what we mean when we ask for the most general antiderivative. And it's just a consequence of that theorem. I'll illustrate this with an example in a moment. But the idea is that every function has not just one antiderivative, but infinitely many. Because you can add some constant to whatever antiderivative you found, and that will be another antiderivative for the same little f. So this language of the most general antiderivative has a specific meaning. It means kind of the basic antiderivative that you find using your anti-differentiation rules, with a plus c written at the end, where c is understood to be what we call an arbitrary constant. A quick example here. Let's say find 3 different antiderivatives for little f of x equals 3x squared. Then state the most general antiderivative. So we're going to find our antiderivative of this function using that power rule I shared with you last time, or if you like, just by kind of thinking about how you could differentiate something to get this. And then I'll give you actually a few different antiderivatives to illustrate the point we made on the previous guy and show you what I mean by the most general antiderivative. So since the derivative of x cubed we know is 3x squared, each of the following are antiderivatives for little f equals 3x squared. I could say just x cubed. We'd say x cubed minus 27 I could say x cubed plus 9. All of these are antiderivatives for 3x squared. If you differentiate x cubed, you get 3x squared. If you differentiate x cubed minus 27, you get 3x squared. If you differentiate x cubed plus 9, you get 3x squared. And I could list more and more and more of these just by adding or subtracting some other constant after the x cubed. It's the x cubed that is the important part here, right? So we say the most general antiderivative is x cubed plus c, where c is an arbitrary constant. Arbitrary just means I don't care what it is. Could be anything.
So question, it could be anything. It doesn't matter what number it is.
As long as it's a constant.
Okay, got it.
Yep, so we could talk about x cubed minus e or x cubed plus pi squared. All of those would be antiderivatives, and they're all captured by this single expression. So because I don't want to wear out my hand by writing the many antiderivatives of 3x squared, we just try to write the whole family of them down at once like this. There is go ahead.
Is there like a clear way to write out how you're finding the antiderivative? Like you wrote the f of x equals 3x squared, and then you just wrote the antiderivatives underneath. There's no sort of like capital F of x is anything until you get to the most general?
There are, so I want to make sure I understand the question. Are you asking how I came up with the x cubed? Is that the thing? Because once we know the x cubed, it's like, okay, just write plus c after that.
I guess. I mean, I remember you wrote out the summary rules last class of the 3x squared. The derivative of x cubed would go to the 3x squared. I'm just confused as to like what's the best way to organize finding these antiderivatives, I guess.
Let me see if I can answer that with a nice we'll call it a theorem. And this is the power rule for antiderivatives. So this is one of the antiderivative formulas I gave last time, but maybe a close look at this will help. So if little f is x to the n, then big F will be 1 over n plus 1 times x to the n plus 1 is an antiderivative. So this is sort of the rule that I'm applying there, if you like. And the proof of this guy is also nice and neat. If we look at the derivative of the thing I claim is an antiderivative, I should get this. So that would be the derivative of 1 over n plus 1 times x to the n plus 1. And this 1 over n plus 1 term here, this is a constant. So he will just pop out. And then all that's left to do is to differentiate x to the n plus 1. And by the regular power rule, the power rule for forward derivatives, the 1 over n plus 1 just hangs out. The derivative x to the n plus 1 primed is n plus 1 times x to the n plus 1 minus 1, which is just x to the n. And then these two guys cancel schmancel, and we just get our x to the n, which is little f. So if your function you're trying to anti-differentiate is a power function, this will work really well. The only caveat is, let me see. Let's say it up here. Suppose n is not equal to -1. The only case this doesn't work is for x to the -1, where we need a different rule there, because the natural log is the function that has derivative 1 over x, or x to the -1. So the way I came up with the x cubed there is by taking this 3x squared. Ignore the 3 for a minute. I just worry about the x squared. That's x to the n. So his antiderivative should be 1 over n plus 1 times x to the n plus 1. That's going to give me 3 times 1/3 times x cubed. And the 3's and 1/3s cancel, and that's where I get my x cubed from. Is that kind of what you're asking, or am I missing the question a little?
That helps a lot.
Okay.
That pretty much answers it.
All right, then. There are other rules like this, but unfortunately, most of the other rules are more complicated, like the backwards product rule. There is like an antiderivative product rule, but it's called integration by parts, and it's something that we don't do in this class. You don't learn it until Calc 2. There's a backwards chain rule, and we are going to learn that. But again, it's a little complicated. It gets its own section in the textbook. It's called U substitution. So besides the power rule, the only other kind of big results we have on antiderivatives is that anti-differentiation is also linear, right? All of these operators we've been playing with are linear operators, and that's a big part of what makes them so nice. The way the book says this, it's another theorem. I'll call this the linearity of antiderivatives. This just says if you want to take an antiderivative of a combination of functions, like some stuff added up or multiplied by numbers, that you can do it one piece at a time, and you can ignore constant multiples. So one way to say this is if big F and big G are antiderivatives for little f and little g, respectively, then some constant times big F of x, we'll call it C1, plus some constant C2 times big G of x will be an antiderivative for C1 little f plus C2 little g. And again, the proof is immediate. We just want to show that the derivative of this is this. So we will get C1 big F plus C2 big G, all primed by the linearity of the regular derivative. This is C1 big F primed of x plus C2 big G primed of x. And since big F is an antiderivative for little f, this is C1 times little f. since big G is an antiderivative for little g, this is C2 times little g of x. So the derivative of this thing is this thing. In other words, this is an antiderivative for this, which is what we wanted to show. Putting the two rules we just discussed together, you can find antiderivatives for any polynomial or linear combination of power functions. I'm going to give you one more little theorem here, and then we'll dive into a few problems. Big F of x equals natural log absolute value of x is an antiderivative for little f equals 1 over x on the set negative infinity to 0, union with 0 to infinity. In other words, everywhere 1 over x is defined, this thing serves as an antiderivative. On the positive reals, on 0 to infinity, I think it's fairly straightforward. If x is greater than 0, then big F of x is the ln of the absolute value of x, but x is positive, so the absolute value of x is just x itself. So this is just regular old natural log of x. So big F primed would be the derivative of regular old natural log of x. And we know that that is 1 over x. So that's equal to little f. On the other hand, right, so this takes care of big F being an antiderivative on 0 to infinity. The absolute values are the things that generally make people scratch their heads here a little bit. And the reason we have to do that is because we claim that this thing also works as an antiderivative from negative infinity to 0. In other words, where x is less than 0. Now, if x is less than 0, then the absolute value of x is the negative of x. Right? That's what absolute value does. If you're positive, it leaves you alone. If you're negative, absolute value multiplies you by -1 to make you positive. So big F would be the natural log of negative x has derivative big F primed by the chain rule 1 over negative x times the derivative of negative x, which is -1. So those negatives cancel, and again we get 1 over x, which is just little f. So together these three things, the power rule, antiderivatives being linear, and an antiderivative for 1 over x, between those three things, we can now anti-differentiate any combination of power functions, any linear combination of power functions. And sometimes this is easier than it might look. Sometimes it's much harder than it might look, and there's algebra tricks that will help. So the main point of this section is to explore the algebra tricks that you're going to need. Let's do it. So I'm going to try to combine all this stuff. Let's say find the most general antiderivative for little f of x equals, how about 3 times the square root of x minus 2 times the 5th root of x. The trick, use the power rule, use linearity. I can write little f as 3 times x to the 1/2, right? This is 3 times the square root of x minus 2 times x to the 1/5. That's the 5th root of x, x to the 1/5. The power rule says is that x to the n has antiderivative 1 over n plus 1 times x to the n plus 1. And we know that constant multiples just come along for the ride. We know that you can split up over addition and subtraction. So this means that big F of x, the antiderivative should be 3 times. I'm going to add 1 to this power and divide by that new power. So n for this guy is 1/2. N does not need to be a whole number. If I add 1 to 1/2, I get x to the 3/2. And that means I also need to divide by 3/2. All right, 1/2 plus 1 is 3/2. And then minus 2 times, I do the same thing with x to the 1/5. So if I add 1 to 1/5, I get 6/5. And then I need to divide by 6/5. And generally, you want to clean up these fractions because this is a pretty horrendous looking thing. I'm looking for the most general antiderivative, so I'm also going to slap on my plus c here. Right, because we could have any arbitrary constant added on. So what do I get here? I've got 3 times 1 divided by 3/2. Well, 1 divided by 3/2, that's 2/3. I'll take my time doing this. This is 3 times 2/3 x to the 3/2 minus 2 times, same sort of thing here. 1 divided by 6/5 is 5/6. And plus c. The 3's cancel in the first expression. The 2 and the 6 can talk to each other, canceling this into a 3. So I'm going to get 2x to the 3/2 minus 5/3 x to the 6/5 plus c. The good news about antiderivatives is that you can always check your work. How would you check an antiderivative? Suppose I'm wondering, did I fuck something up? Is this the correct antiderivative for this? What would I need to do to this thing to verify?
Take
Would
the
you take the
derivative of it.
derivative?
Mhm. So if I want to check my work, you just differentiate. And this is not so bad right now. It can be a bit of a headache when things get more complicated, but it always works. I'll do it here. Big F primed would be parentheses 2x to the 3/2 minus 5/3 x to the 6/5 plus c all primed. We've done so much of this at this point, it should be very quick now. So this is 2 times 3/2 x to the 3/2 minus 1 is 1/2 minus 5/3 times 6/5 times x to the 6/5 minus 5/5 is 1/5 plus the derivative of a constant is 0. Cancel the 2's, cancel the 5's. 6/3 is 2. We get 3x to the 1/2 minus 6/3 is 2x to the 1/5. And is that what we started with? Yes, it is. can declare victory. And there's something reassuring about this, right? You can always check your work. The trick to this problem, of course, was rewriting the radicals as powers. And then once you have a straight up power of x, we know how to take an antiderivative of those. But these problems can be made more complicated if they're not given to you in that form. Let's try something like that. Often in mathematics, when we learn a new rule and we go to apply it to a new function, it's tempting to apply the rule to kind of every piece of the function at once. That works in certain situations, right? Like we know that derivatives and antiderivatives are linear. So you can split up over addition or subtraction. You can pop out constant multiples. But here I'm dividing this polynomial by x. So this is not a constant multiple. This is not addition or subtraction. So I want to make a quick note. Big F is not what you would get by anti-differentiating each piece. So 3x, it's not going to be x cubed minus x squared plus 7x over 1/2 x squared. This ain't going to work. You can't just take the antiderivative top and bottom. What will work though, right? We can't anti-differentiate top and bottom separately. And that should make sense, right? You can't take derivatives top and bottom separately. That's why we have the quotient rule. So there are things like a backwards product rule, backwards quotient rule, backwards chain rule that you have to learn for antiderivatives. We don't need that here, though. We just need some algebra. All we have at this point is the power rule stuff. So the only way I could hope to find an antiderivative here is by rewriting this function as powers of x, just straight up powers of x. And I can do that if I split up the fraction. This is 3x squared over x minus 2x over x plus 7 over x. This sort of stuff works. The algebra rule, just that fractions like a plus b over c can always be split up as a over c plus b over c. Just algebra. Now we simplify. X squared over x is just x, so this is 3x. 2x over x is 2, so this is minus 2, plus 7 over x is 7 times 1 over x. Now I've got straight up powers, constants times powers of x that I can apply my rules to. The constant term 2 here might throw you off for a little bit. If you think critically, pause for a second, think critically, ask who has derivative 2, you realize it's 2x. You could also think of this 2 as 2 times x to the 0 if you wanted. And then your power rule does work when n is equal to 0. It says add 1 to the power, so the power would become x to the 1, divide by the new power. But however you like to get there, big F, my antiderivative. I take 3, bring him along for the ride, and then apply my power rule here. This is x to the 1. So I'm going to get 1/2 x squared, right? 1 over n plus 1 times x to the n plus 1. Minus 2x, right? If you like 2 times 1 over 1 times x to the 1, just write 2x. Plus 7 times, what's the antiderivative for 1 over x?
Is it natural log?
Yeah, the natural log of the absolute value of x plus. So this piece became this stuff. This piece became this. And this became this. It's not too bad. The lesson here is one that we've bumped into many times. If you can clean up the original thing with algebra, always do that before attempting the calculus. All right, if you can do some algebra to make your function prettier, simpler, whatever, do that shit. Do that shit before trying the calc. It will make your life so much easier. And then, of course, this warning, just like you don't take derivatives top and bottom separately, don't try to take antiderivatives top and bottom separately. Everything that you kind of can't do with regular derivatives, you also can't do with antiderivatives. Very similar in spirit like that. Questions on these examples? Okay. All right. It's hot out there too. Oh, it's better than it is in here. All right. Oh. Let's find the most general antiderivative for the square root of x times x squared minus 2. Definitely power function, power function, power function. I know how to anti-differentiate power functions. But again, I can't just dive in and anti-differentiate, anti-differentiate, anti-differentiate and call it a day, because these are being multiplied. If I was going to differentiate this, I would have 2 options, either product rule, as it is now, or multiply it out and then use the power rule. I don't have an antiderivative product rule yet. Again, that's called integration by parts, and you will learn it in Calc 2. So the only attack that we have is to multiply it out first. So that same shit, just do the algebra first, right? Clean it up first. So first we're going to rewrite f of x as root x times x squared minus 2 times root x, which is x to the 1/2 times x to the 2 minus 2x to the 1/2. And then I need to write these as a single power of x. That's x to the 2 plus 1/2 is 5/2. minus 2x to the 1/2. So my most general antiderivative, capital F here, can now be found using the power rule. All right, now that I have individual powers of x separated by addition or subtraction, maybe with constant multiplying, but no variables multiplying, no variables dividing. Add 1 to the power, divide by the new power. So 5/2 plus 1 is 7/2. So this is going to be 1 over 7/2 times x to the 7/2. That's the antiderivative of this piece. Minus 2 times 1/2 plus 1 is 3/2. So this is going to be 1 over 3/2 x to the 3/2, and we write our plus c. There is a pattern to these things. After a while, you're going to get tired of writing stuff like this. You'll realize that you always just get the reciprocal of the power. So at some point, you will be jumping straight to expressions like 2/7 x to the 7/2 minus, here I'd have 2/3. So 2 times 2/3 is 4/3 x to the 3/2 plus. There is one antiderivative that is so simple and straightforward. I haven't mentioned it. I actually completely forgot to mention it, but it should be everybody's favorite. Let's see if we can get there without stating it as a theorem. How about 6e to the x minus 4? We never talked about an antiderivative for e to the x, but you know that when you differentiate e to the x, it stays e to the x. So if you're looking for somebody who has derivative e to the x, that would be e to the x itself. So again, using linearity, the antiderivative for 6e to the x is 6e to the x, because if you differentiate this, you do get this. And then the antiderivative of 4 is 4x. All right. I don't want to beat you guys down with more of this antiderivative stuff at this point, but I do want to leave you with a few head scratchers. Before I depart, any questions on either of these two examples here?
Would you add a plus C at the end of that?
Oh,
Also?
yes.
Oh,
Yes,
okay.
yes. I lose a point. Damn. Yeah, and this is like the tacky thing. I hate doing it, but I've got to take off points on these where you don't write a plus C. It's so easy to forget. So I appreciate the catch there. It's a good teachable moment. After you solve one of these problems, stop and ask yourself, did I write plus C? This is tempting to forget, because of course it's not really something you think about, but it is something that we're required to take points up for. Good catch. Are there other questions or comments on this? Okay. So some fun antiderivatives for you to think about. Can we find an antiderivative for a slightly modified exponential like e to the ax? Or sine of ax? Or cosine of ax? Right, take any of those transcendental functions that we know the antiderivative of and just put a little constant inside. I should say non-zero. So if a is 0, then these are all constant functions. That's boring. But this is technically a backwards chain rule thing, which is technically called U substitution. But technically, they're not hard, and you can figure them out if you think about them. And I think thinking about them before we get to the section on U sub will really help you understand what we're doing with U sub. So think about what the regular derivative of this function looks like, and then think about how you would undo that. I promise it's not anything hard, and I promise if you spend a few minutes just thinking about this question before we get to section 5.5, that section, which is infamously challenging for Calc 1 students, will feel much easier for you. So I'm not going to solve these for you. I want you to think about this. It's not homework, it's not a grade, but if you think about this, it will make your life easier, and I promise it'll take you all of 10 minutes to do, so why not? That's on the nice side of things. On the evil side of things, let's start with x e to the x, or x sine x. Anything that is fun for e to the x is fun for sine and cosine, or x cos x. Like I said, this is slightly evil, slightly evil. I will not in this class be teaching you how to find antiderivatives of these functions. Differentiating them would require a product rule, so anti-differentiating them requires an anti-product rule. If you've got extra time, spend a little bit of it trying to think of how one might anti-differentiate these. Not obvious. Not obvious, and I do not require it, nor do I expect it of you in this class, but I think it'll be fun to think about if you have the extra time. Straight up evil shit. Or, again, what works for sine e to the x, works for sine or cosine? Something like sine of x squared or cos of x squared. These are quite famous. This is called the error function, the Gaussian bell curve. These are known as Fresnel functions from Fresnel integrals or Fresnel curves, if you're familiar with the concept from physics. I could go on and on like this. Natural log of x over x. Oh, actually, no, this one's not bad. I take this one back. E to the x over x sine x over x cos x over x. I'll just tell you, these are impossible. Another one that it's impossible is x over ln x. Not only do you not know how to do these, nobody knows how to do these. So when I said that at first we get the idea that taking antiderivatives is like the same as taking derivatives but backwards, that's somewhat true, but it's also somewhat not true, in the sense that I can take the forward derivative of any of these functions. Differentiating these, not bad, right? Chain rule, quotient rule. But finding an antiderivative for any of these using any finite length expression in terms of sines, cosines, powers of x's, square roots, exponentials, impossible, impossible. At the end of Calc 2, at the very end of Calc 2, I will show you antiderivatives for these. They involve expressions that are infinitely long, called power series. These are medium hard. And these are not bad at all. So the top row, again, I will show you in section 5.4. Thinking about it ahead of time will help you understand 5.4. I encourage everybody to spend some time on these. These, if you got the spare time to grind on it for a little bit, have fun. Try taking forward derivatives and see what that does, and think about how you might get rid of some of the weird stuff that happens from the product rule. It's a great exercise. It'll help you when you get into Calc 2. These, I don't bother, right? Just be aware that there is shit out there that is really hard to anti-differentiate. And we could keep going, right? This list goes on and on and on. Okay. Antiderivatives, exciting. Anytime you're writing down things in math that feel very natural and normal and you run into a straight up impossible thing, I think that's exciting. The other thing that we need to talk about today is the apparatus that appears in the fundamental theorem of calculus. Specifically in FTC1, we encounter this function g of x that was defined as the integral from a up to x of some other function. What I want to do is compute, given a function little f of t, I want to compute several values of the function g of x. So we're going to pivot back to FTC1. I'll say recall FTC1 says if little f of t is continuous and we define g of x to be the integral from a up to x of little f of t dt, then g of x is differentiable and g primed of x, which would be d dx of the integral from a to x of little f of t dt, is just going to be little f of x. So this is the full statement of FTC1, and I've included here an alternate notation. Oftentimes you just see g primed equals little f of x. I want to include this because sometimes you'll see problems that ask you to compute something like this, and you just have to remember, oh, that's the same as this. That's the same as this. We've already discussed FTC2 enough so that if I was to give you an algebraically defined function little f, we could take its antiderivative, plug in bounds, and then differentiate. That's boring now. What I want to do is give you a bit of exposure to what functions defined in that fashion do. First, the hypotheses. We required that little f be continuous, and g was defined to be the integral of little f. That means that integration is somehow a smoothing process. When you integrate, you can take a continuous, but perhaps not differentiable function and turn it into a differentiable function. That's a very special thing. More importantly, though, this function g I'll say is the integral, I'll let a be 0, is the integral from 0 to x of f of t dt. where f is graphed below this function g, it's not immediately obvious that it works like an antiderivative for little f, but it does. So let me flag off, like I said, 4. So let's go 1, 2, 3, be generous, 4. This 1, 2. This is -1. We'll finish here at 4, +1. Just to be clear. This is what we're talking about. Oh. So the horizontal axis here is the t-axis. And this is the graph y equals f of t. The big idea I want to get into your head from this is that the symbol t in this integral here is what's called a dummy variable. I could change the t and dt to a z and dz, or y and dy, or your mom and d your mom, and it wouldn't matter. Because what I'm really asking is, what's the area under this bitch from 0 up to the x value you're trying to plug in here? It depends only on the geometry of the graph, not the label of the variable inside. A lot of people get confused or frustrated by FTC1 because it's like, well, the function was f of t. What do you mean f of x? Where is the x coming from? And the truth is that the x is coming from up here. So let me show you. I want to begin by computing g of 0. And that means, remember, this is the function g of x. So that means I'm plugging in 0 for x. So that's the integral from 0 to 0 of f of t dt. One of the properties that we have for the definite integral is if you integrate any function from a to a, if these upper and lower limits of integration, or sometimes called bounds of integration, if those are the same number, you're always going to get 0. You can see that in the context of the graph here, because I'm asking what's the area bounded by this function from x equals 0 to, from t equals 0 to t equals 0. What's the area here between 0 and 0? Well, there's no area there. It's got no width to it, so it can't possibly have any area. Someone from Santa Fe is calling me. One moment. Professor Fosticker. Hey, Dan, I'm doing okay. I hate to do this, but I'm actually in the middle of a lecture right now. Can I call you back in a few minutes? All right, I'll give you a ring in about 20 minutes. Bye. I had to report a few students for cheating recently, so that's Dan Rodkin calling to catch up. Okay, integral from 0 to 0 of anything would always be 0, because there is no area between 0 and 0 here. So g of 0 is 0. G of 1 would be the integral from 0 to 1 of f of t dt. So now I do have something to think about. I'm looking for this area, right? This pencil shaded area here, that's the integral from 0 to 1 of f of t dt. I'm taking the area between 0 and 1 underneath the graph. I drew this as a piecewise linear function, so we can use basic geometry. We do 1/2 base times height. The base here is 1, the height here is 2. So this is 1/2 times 2, which is 1. G of 2 is the integral from 0 to 2 of f of t dt. Which means now I'm looking for all of the shaded area from here to here. So I need the area of the full triangle up here, and that will be measured as positive because it's above the horizontal axis, minus the area down here. Now, in order to do that, I need to know this intersection point. We're coming from 1, 2 down to 2, -1. So the slope here would be a -3, and the divided by that run here, which is 1. So the slope is -3. That's going to tell me that this intersection point here is at not 1.5, right? Not 1.5, but 1 3/4. Or label that. Uh, 1.25, so 1.75, or 1 3/4, which would be 7/4. So then I take the area of the big triangle there, which is 1/2 times 7/4 times 2.
I'm so sorry. Can you just tell me really quick how you got that again?
Oh, basically what I'm thinking is this thing's going down at a constant slope. It needs to come down 3 over a width of 1. So because it's going to have to do 2/3 of that here and 1/3 of that here. Sorry, 3/4 of that here and 1/4 of that here. You can pretend like it's 1/2. If you want to say that I just made this up, you could say that too. There's really no calculation going into it.
Oh, okay. Thank you.
What is it? Okay, so the area of the big triangle here would be 1/2 base times height. The height is still 2, and the base here is 7/4. So the 1/2 and the 2 cancel, and you just get 7/4. G of 3 would be the integral from 0 to 3 of little f of t. Oh, wait, no, I didn't finish. Sorry, we'll come back to this. We still need to subtract off the area of the little triangle down here. So here my base is 1/4, and my height is, if you think of it in terms of areas, this would be like 1/4 times height 1. And we are subtracting because we're beneath the horizontal axis. So that's again a triangle, 1/2 base times height. The base is 1/4, and the height there is 1. So now simplifying, this is 7/4 minus 1/8. And that's what, 14/8, so 13/8 altogether. If I want to find G of 3 now, that's going to include out to here. And this gives me a nice opportunity to share with you another property of the definite integral. Would you agree that this total pencil shaded area here is this area plus all this little area plus this area. In other words, it's the area we just found, big triangle minus little triangle, plus this little rectangle area. So you can do the integral from 0 to 3 as the integral from 0 to 2 plus the integral from 2 to 3. I'll state it as
Wouldn't it be negative?
would what this piece will certainly be negative, and this piece is negative. This piece is positive. So if are you asking about the piece from G of 2?
No, we're on the same page. You were just saying adding it. So wouldn't you like subtract
sorry,
it?
yes, you're right. I would be adding it, but the thing I'm adding is negative. So we could say subtracting, yeah. So the slick way to do this is to take the integral from 0 to 2 and add to that the integral from 2 to 3. Right? This is all the area from 0 to 2. This is the area from 2 to 3. And together, those will give me all the area from 0 to 3. The integral from 0 to 2, I just computed, that's 13 over 8. The integral from 2 to 3 is just this rectangular region here, which is width 1, height 1, right? But he is beneath the horizontal axis. So this is actually a square of area 1. And 1 is, of course, 8/8. 13 minus 8 is 5. So this would be 5/8. And then finally, to get the integral from 0 to 4, I need to add to what we just found the values that come from these shaded regions. Here you can make use of a symmetry argument. Right? This line is going from down here at -1 to up here at +1 over an interval of width 1. So this is a slope 2 line going over width 1. So he's going to intersect halfway through here, which means that this triangle has the same area as this triangle. 1 is beneath the horizontal axis, the other one is above. So I'll begin by saying G of 4 is the integral from 0 to 4 of f of t dt. And I would split that up as the integral from 0 to 3 of f of t dt plus the integral from 3 to 4 of f of t dt. And the fun observation here is that this is 0 by symmetry. The stuff down here would be measured as negative, right? This would be negative 1/2, right? Or negative 1/4. And the stuff up here would be measured as positive. This would be positive 1/4. So they'll cancel out perfectly. So this is actually going to be the same as the guy that we had from the previous part, 5/8. The thing that I think is a little bit hard to wrap your head around is that this new function g is the signed area bounded by f from 0 up to x. It's just weird having a variable be one of the limits or bounds for your integral. Let me see if I have. Actually, I might be one already made up. FTC1. That's shitty. All right, I will put together a Desmos environment for you guys. I don't want to burn time in class here, where you can play with these outputs. There's two things that we kind of are exposed to here that I want to now generalize a little bit. One is this rule for splitting up or combining integrals by splitting them up over the bounds, sort of. The other thing I'd like to do here is look a bit at the graph of g of x. This is the graph of f of t. And I want to point out a few things. First, this function is not differentiable, right? It is not differentiable at 1. It is not differentiable at 2 or 3, because it's got these hard corners there. And we know that hard corners, sharp edges, make functions not differentiable. I claim that g is differentiable. According to FTC1, g should be smooth. And I have some values for the function g here. It might be fun for us to try and sketch the graph of g. So having done this, let me record those up there somewhere nice. G of 0 is 0. G of 1 was 1. G of 2 was 13 over 8. G of 3 and G of 4 were both 5/8. Okay. So the next thing I'd like to try to do is to try and sketch the graph of g from the graph of f here. And we can use what we just found, these points. Imagine it will be useful to have a feel for how big 13/8 and 5/8 are. So 5/8 here is 0.625. I'm just going to approximate that as 0.6. And 13/8 will approximate that as 1.6, just to give us a rough feel. Now we're going to sketch the graph of g. Let's start by plotting points. We know that g of 0 is 0. That means the graph of g starts here at the origin. As x increases through here, the amount of area captured is increasing, and it's increasing quickly because f is itself increasing. Even if f was constant, g would be increasing quickly there. The fact that f is itself going up means that not only is the area increasing as x scoots to the right, but it's increasing at an increasing rate. In other words, concave up. So from 0 to 1, g should be growing quickly, concave up, and we reach the max, well, we reach it, not a max, but we reach the point 1, 1. Let me mark this as 1 on the y-axis and 2 on the y-axis. We get here to 1, 1, and we get there quite quickly. As x increases past 1, now I'm looking at like all of this area, g is still getting bigger, right? If x is over here, then as x continues scooting to the right, I'm still capturing more and more area, which means this function is still increasing. But the amount of new area I get every time x increases a little bit is getting less and less. So now I'm increasing, but I'm concave down. So I'm going to reach an inflection. This is going to be an inflection point where I change from concave up to concave down. And this x value right here, 7/4, that is going to correspond to a max. The total, the height at 7/4 there, I think we did calculate that as a part of one of these. Yeah, is going to be this, is going to be 7/4 itself, almost 2. And then by the time as we go past 7/4, now we're picking up some negative area. So if you imagine X is over here right now, we've totaled up all this area. But now the area we're picking up between here and 2 is negative, which is going to start subtracting from the value of G. So as we go past 7/4, this is going to turn around. And right here at 2, we have a point, 2, 1.6, or 2, 13/8. But notice that there being a sharp point here doesn't mean that there's a sharp point here, or actually it would be here at 1, because this doesn't have any dramatic effect on how much total area is underneath there. It just means, okay, well, you're adding area less quickly now, which means you go from concave up to concave down here. By the time we get to 2, we know we're back down to 1.6. When we get to 3, we're all the way down to 0.6. So all this negative area is subtracting. And by the time we get over here, we're just a little bit bigger than 1/2. As we come past, this is actually, I shouldn't have drawn that as having a horizontal tangent line. We're still going downhill here, because as we go past 3 now, we're still adding in more and more of this negative area. Imagine your X is like right here, a little bit past 3. The area that we're adding from 3 to this X is still negative, so we're still going downhill here. And then exactly at this point, right here, 3.5, we switch to adding positive area. So this is going to be a min on the graph of G. So we start going back up because now we're adding positive area, and that would be the end. Pretty cool, right? Now, if I gave you this, and I said, sketch for me a graph of the derivative of this function. That function would be positive everywhere to the left of 7/4, yeah? Because this function is increasing everywhere to the left of 7/4. Well, look at this, positive everywhere to the left of 7/4. That function would be increasing from 0 to 1, because I'm concave up from 0 to 1, increasing 0 to 1. That function would be positive but decreasing from 1 to 7/4, because I am increasing but concave down, positive but decreasing. That function would be negative from 7/4 all the way to 3.5, because my function here is decreasing, his derivative should be negative. Well, this guy is negative from 0 to 3.5, and then positive again from 3.5 to 4. This is the derivative of this, which means this is an antiderivative for this. Observe. Just from graphs, it appears that G prime is F. And I'm leaving the variables out because I don't want you to get confused. It looks like the derivative of this thing should be this thing, and that is the truth. That is exactly what FTC1 says. FTC1 says that G prime of X should be little f of X. And that's what it fucking looks like to me. So this is what I wanted to share with you. It's going, like so many other things in this class, and I'm sorry if it's sounding repetitive, it's going to take some time to really get comfy with this stuff, but it is possible. It is very possible. There are a handful of homework problems in your assignment for this week that have you doing precisely this. And as you solve those, really take your time on them. Draw the graphs, shade, consider sketching the graph of G, even if you're not told to, and especially if you're told to, draw this graph by hand. All right, that's something that we've said over and over again. Every time web assigns like draw a graph, it's like, well, fucking click one of these graphs. Great, we can try it 4 times. And even if we don't even draw anything on our page, we'll get it right. Don't do that to yourself. Take the time. It doesn't have to be art, and it might not match what WebAssign gives you exactly, but spending the time trying to come up with this from this, following precisely the logic we did here, you'll get where you need to be. And that's what I really want for you guys, is to see those two things in context. Next time, I'm going to talk about how the chain rule interacts with FTC1, right? So that is how you sort of combine the differentiation rules that we've seen in the past with this idea that you can differentiate a function defined as an integral. That turns out to be a tiny bit complicated, and the right way to see it is by applying FTC2 and then taking a derivative. You'll see what I mean. The other thing I'm going to do on Friday is just give you practice calculating definite integrals using the mechanisms of FTC2. What else did we want to say? Antiderivatives. So I gave you formally an antiderivative rule today. There are other antiderivatives that you should know. Every derivative that you know corresponds to an antiderivative that you should know. And I went looking through your book in 4.9 for a nice table of all the antiderivatives you ought to know. And I did not see it in here. Here are a few, but we want more. So I think we may have to go down to the section on indefinite integrals. So let me share this with you. We have not talked about 5.4. We will not talk about it this week, but this is the place where you can find your nicest collection of antiderivatives for this stage in the class. So if you're looking for somewhere you can go to make flashcards, this would be a good thing. The integral without bounds just means most definite antiderivative. That's literally all it means. There's other content in this section, and we will approach it on its own. But we've been through several of these, right? Like all of these we've been through. We've been through the sine, cosine, secant squared, secant tangent stuff. I didn't give you these the other day, but these two you want to know as well. So if you're looking for somewhere you can kind of look up antiderivatives, this section, section 5.4 on page 403 in the text, is the way to go for now. But you should be able to reason your way there just by thinking about the regular derivative rules. And yeah, that's it for me. Any burning questions before I let you guys go?
Hello.
All righty then. I will go ahead and end the meeting here. Hope you guys have a lovely rest of your day. Work hard on that homework, and I'll see you on Friday.